Okay, so you know how everyone thinks trigonometry is all about triangles? Like it's just that one thing you do in high school geometry and then never see again.
Right.
But honestly, it's kind of mind-blowing how much stuff actually relies on triangles. It's way more than just triangles.
Oh, absolutely.
I mean, think about it. We're talking predicting earthquakes like in seismology, or designing all the crazy complicated circuits in your phone,
Yeah.
even describing how atoms behave,
Yeah.
which is like a whole other level of weirdness.
It's true.
And then there's stuff like how ocean tides work and even what makes a musical note sound the way it does.
It really is incredible how these core mathematical ideas end up being so important in such different areas.
Totally. So for this deep dive, we're going to focus on trigonometric functions themselves. You know, the sine, cosine, tangent things.
Right.
The stuff you sent me starts really basic, like what even is an angle and how do we measure them?
Yeah, it builds up really nicely.
And then it goes into all these really useful equations and identities that help us do cool things with trig.
Yeah. It's a very logical progression from the ground up.
Exactly. So our goal here is to make you really comfortable with these functions, like not just memorizing SOH, CH, TOA from right triangles,
Right.
but actually understanding like the big picture of how they work and why they're so powerful for describing the world.
That's the key.
And we'll try to do it without getting too bogged down in all the crazy math details.
That's the goal. Make it intuitive.
Exactly. So let's start with something that seems simple but is actually super important. Angles. Now, the source defines an angle as basically how much a ray rotates around its starting point, which is called the vertex.
Right. So it's all about rotation.
Picture like this second hand on a clock sweeping around the face.
Mm-hmm.
That second hand is like the ray, and the center of the clock is the vertex.
That's a great analogy.
Now, the direction of that rotation matters.
Huh?
If it goes counterclockwise, like opposite the way most clocks go, that's a positive angle.
Okay.
But if it rotates clockwise, like a normal clock, that's a negative angle. Figure 3.1 in the source shows this really clearly.
Visuals always help.
Totally. So we've got the direction figured out.
Okay.
But now we need to measure how much that ray is actually rotating.
Right. How big is the angle?
Exactly. And the source talks about a few ways we can do that.
Okay.
One way is with revolutions, which is pretty intuitive. Like, think about a spinning propeller on a plane.
Makes sense.
One full turn of that propeller is one revolution.
Easy.
Yeah, but for most math stuff, we use degrees. A degree is just 1/360th of a full revolution.
Okay. So 360 little slices in a full circle.
Exactly. And each slice is 1 degree,
Yeah.
written like this. 1 with a little circle up top. That's the degree symbol.
Got it.
Now, the source goes even deeper and says that each degree can be broken down into 60 minutes.
Oh, wow.
Yeah, kind of like how an hour is divided into minutes.
Yeah.
It's written with a little apostrophe. So 1 minute is 1 foot,
Okay.
and then each minute is made up of 60 seconds, so like with time. And a second is written with 2 little apostrophes. So 1 second is 1.
Okay, I see. So it's degrees, then minutes, then seconds, just like time.
Exactly.
It can get a bit confusing, but it's a system that's been used for a long time, so it's still important to know.
Makes sense.
Now, figure 3.3 in the source gives us some visual examples. Like a full circle is 360 degrees, a half turn is 180 degrees, a 3/4 turn is 270 degrees,
Okay.
but you can also have angles bigger than a full circle, like 420 degrees. That's just a full circle plus an extra 60 degrees.
Oh, interesting.
Yeah, and of course they show negative angles too, like negative 30 degrees or negative 420 degrees.
Right, because that just means we're rotating clockwise.
Exactly. What's cool is that these visuals show us that angles aren't just stuck inside some triangle. They can be about any rotation, no matter how big or small, or even in what direction.
That's a good point. It's dynamic.
Yeah. But now get ready for this, because while degrees are what we use in everyday life, radians are the real MVP in a lot of math, especially when trig meets other fields like physics or engineering.
Radians, okay.
Yeah, so radian measure connects angles and circles in a really elegant way. 1 radian is defined as the angle you get at the center of a unit circle when the arc along the edge of the circle is the same length as the radius. Hold on, I need to picture this. A unit circle is just a circle with a radius of 1, right?
Exactly. So imagine you've got this circle with radius 1. Now picture a slice of that circle where the curved edge, the arc, is also exactly 1 unit long.
Okay, I'm picturing it.
The angle formed at the center of that slice, that's 1 radian.
Oh, I see. So it's like the angle opens up just enough to perfectly match a piece of the circle's edge. It's the same length as the radius.
Precisely. And because the whole circumference of any circle is 2 times the radius, and for a unit circle the radius is 1, a full revolution around the circle is 2 radians.
That's where the pi comes in.
Exactly. It's baked right into the definition, which is why radians work so well in a lot of formulas.
Makes sense.
Now here's a super handy formula that works for any circle, not just a unit circle. You've got a circle with radius r, And an arc along its edge has length O.
Oh, okay.
And that arc makes an angle theta at the center of the circle.
They use Greek letters for angles, huh?
Yeah, theta is a common one. So the formula says that the angle in radians theta is simply the arc length divided by the radius. Theta equals L divided by R.
Okay, so theta equals L over R.
Exactly. Or if you know the angle in radians and the radius, you can use it to find the arc length. L equals R times theta.
So L equals R theta. Got
So-
it. It's like they're all linked together.
Exactly. This formula is super useful, so it's definitely worth remembering.
I'll try to.
Okay, now get ready for this next part because it's kind of mind-bending. The source explains how radians are actually connected to real numbers, like 1, 2, 3 negative numbers, all those.
Really? How does that work?
So picture our unit circle, again, centered right at the origin of our xy coordinate system.
Okay.
Now imagine a straight line just touching the circle at one point. It's called the tangent line,
Okay.
and the point where it touches is called point A, and it represents the number 0.
Okay, so we've got a number line and a circle touching at 0.
Now here's where it gets trippy. If you take the positive part of the number line and wrap it around the circle counterclockwise,
Yeah.
every number on that line will end up on a point on the circle.
Whoa.
Yeah, and that point on the circle corresponds to a specific angle in radians.
Mhm.
Do the same thing with the negative part of the number line, but wrap it clockwise.
Okay, so it's like I'm taking the straight number line and coiling it around the circle.
Exactly. The source uses the word roping, which I think is a great visual.
It is.
So basically, every real number can be thought of as an angle in radians.
That's so cool.
Yeah, it connects these two totally different ideas in a really elegant way.
It does.
Okay, so now that we've got radians down,
Right.
let's talk about converting between degrees and radians because we need to be able to switch back and forth.
Right. Makes sense.
Remember how a full circle is 360 degrees?
Yeah.
And it's also 2 radians.
Right.
So that means 2 radians equals 360 degrees. And we can simplify that to radians equals 180 degrees.
Okay, that's a key relationship.
Exactly. And from there, we get our conversion formulas. To turn degrees into radians, you multiply by over 180.
Okay.
And to go from radians to degrees, you multiply by 180 over k.
Got it.
They even give us some rough equivalents. 1 radian is about 57 degrees and 16 minutes.
Okay.
And 1 degree is about 0.01746 radians.
So tiny.
Yeah. And there's this super useful table in the source that shows the exact conversions for common angles, like 30 degree, 45 degrees, 60 degrees, 90 degrees, all the way to 360 degrees.
Oh, that's handy.
Definitely. It's worth taking a look at it and maybe even memorizing some of them.
Good idea.
Now, one important thing about notation. When you see an angle with that little degree symbol, it's obviously in degrees.
Makes sense.
But if you just see a number or an expression with 3 or 2, it's usually assumed to be in radians.
Ah, so you have to pay attention to the context.
Exactly. That little degree symbol makes a big difference.
I'll keep that in mind.
Okay, so to really nail down these conversions, the source walks through some examples. Example 1 shows how to convert 40 degrees in 20 minutes into radians. They first turn those 20 minutes into a fraction of a degree by dividing by 60.
Right, because there are 60 minutes in a degree.
Exactly. Then they use the degree to radian formula.
Makes sense.
Then example 2 does the opposite. It takes 6 radians and turns it into degrees. They use the approximation p equals 227 for this one.
Okay.
And they even go the extra mile and convert the decimal part of the degree answer into minutes and seconds.
Wow, detail.
Yeah, then example 3 is a bit more real world, about finding the radius of a circle when, the central angle in degrees and the length of the arc it cuts off.
Oh, interesting.
The key takeaway here is that you absolutely have to have the angle in radians when you use that formula, L equals R theta.
Right, because that formula only works with radians.
Exactly. So the first step is always converting those degrees into radians.
Got it.
The example 4 is super relatable. It's about how far the tip of a minute hand on a clock travels in a given amount of time.
Okay.
They cleverly link the time to the angle the hand sweeps through, and then use the arc length formula, making sure the angle's in radians, of course.
It's a cool application of that formula.
Totally. And the last example in this section, example 5, talks about 2 different circles that have arcs of the same length, but different central angles.
Okay.
It asks about the ratio of their radii. And using L equals R theta and knowing L is the same for both, we see that the radii are inversely proportional to the angles.
That's interesting. So a bigger angle means a smaller radius to keep the arc length the same.
Exactly.
Cool.
Now the source wraps up this intro to angles and measurement by pointing you to exercise 3.1.
Oh, good. More practice.
Yeah, working through those problems is a great way to really get comfortable with converting between units and using those core formulas.
Definitely practice makes perfect.
All right, so now that we've got a good handle on angles and how to measure them,
Yeah.
we can move on to the heart of the matter. trigonometric functions. Now, you probably remember these as ratios from right triangles like SOH, CAH, TOH.
Yes, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse and so on.
Exactly. But the source takes this idea way further and defines these functions for any angle using radians and our good friend the unit circle.
So it's not just about right triangles anymore.
Nope, it's about any angle imaginable.
That's a big leap.
It is. So here's how it works. We put an angle in what's called standard position.
Standard position.
Yeah, just means its vertex is at the origin of our coordinate system, and its initial side is along the positive x-axis.
Okay.
And then we look at where the other side of the angle, the terminal side, intersects the unit circle. We call that point P and give it coordinates AB.
So we're basically seeing where the angle hits the unit circle.
Exactly. And from those coordinates, we can define our trig functions. For an angle of x radians, cosine of x, written as cos x, is just A, the x-coordinate of point P.
Okay.
And sine of x, written as sin x, is B. The y-coordinate P, figure 3.6, shows this visually.
So it's like we're using the unit circle to give meaning to sine and cosine for any angle.
Precisely. And this is way more powerful than just using right triangles, because it lets us work with angles of any size, positive or negative.
That's what makes it so useful for things that are cyclical.
Exactly.
Yeah.
And right away, this definition gives us a super important identity. Because P is on the unit circle, its coordinates have to follow the equation of the unit circle, which is x plus y once 1.
Right.
And since x is cos x and y is sin x, we get cos y plus sin x plus 1, 1. This is like the most famous trig identity.
The Pythagorean theorem of the unit circle.
Exactly. It's true for any value of x you can think of.
Wow.
Now, the source talks about these special angles called quadrantal angles.
Quadrantal angles.
Yeah, they're just multiples of 2, like 0, 2, 3, 2, and 2.
Okay.
They list the sine and cosine values for these angles, which are easy to see on the unit circle because they're where the circle crosses the x and y axis.
Right. Like at 0 radians, which is also 0 degrees, the point on the unit circle is 1, 0. So cos 0 is 1 and sin 0 is 0.
Exactly.
It's all about those coordinates.
I'm starting to see how it all connects. Now, here's where it gets even more interesting. Sine and cosine are periodic functions.
Periodic.
Yeah, it means their values repeat in a regular pattern. Think about going around the unit circle. Once you've gone 2 radians, you're back where you started.
Right. Full circle.
So the values of sine and cosine start repeating. So sin 2 naught plus x is always the same as sin x, and cos 2 naught plus x is always the same as cos x, where n can be any whole number, positive, negative, or 0.
Oh, I see. So it's like a wave that keeps going up and down in the same pattern.
Exactly. And the length of that repeating pattern is called the period for sine and cosine. It's 2 sin.
Okay.
Now, they also point out where sine and cosine equal 0, sin x is 0, whenever x is a multiple of po, like 0, 2, next, tot, and tot, and so on.
Okay.
That's because those angles put the point on the unit circle right on the x-axis where the y-coordinate, which is sine, is 0,
I see.
and cos x is 0, whatever x is an odd multiple of 2, like 2, 3, 2, not 2, 2, 3, 2, and so on.
Right, because then the point's on the y-axis where the x-coordinate, which is cosine, is 0.
Exactly. It's all about those coordinates.
Right. This unit circle is really the key to understanding all of this.
It really is. Now let's bring in the other 4 trig functions, cosecant, secant, tangent, and cotangent.
Right. Those are defined in terms of sine and cosine.
Exactly. Cosecant, written as cosec x, is just 1 divided by sin x. Secant, written as sec x, is 1 divided by cos x. Tangent, written as tan x, is sin x divided by cos x. And cotangent, written as cos x, is cosecant divided by sin x.
Okay, so they're all based on sine and cosine.
Yeah, but that also means they're undefined whenever the denominator is 0.
Right, because you can't divide by 0.
Exactly. So like cosecant is undefined when sin x is 0, and secant is undefined when cos x is 0.
Got it.
Now, just like sine and cosine have their big identity, cos x plus sin x is 1, these other functions have their own identities too.
Oh, really?
Yeah, you can get them by starting with cos x plus sin x was 1 and dividing everything by either cos x or sin x.
Okay.
If you divide by cos x, you get 1 plus tan x is 0 equivalently. And if you divide by sin x, you get 1 plus coto x equals cotec x. These are super useful because they let you switch between different trig functions.
So it's like they're all connected.
Exactly. They're all part of the same family.
I like that.
Now, the source has this handy table that shows the exact values for all 6 trig functions for those common angles we talked about before.
Yeah.
0 degrees,
Mm.
30 degrees, 45 degrees, 60 degrees, and 90 degrees.
Oh, nice.
Yeah, it's a great reference. It's really helpful to know these values or at least be able to figure them out quickly using the unit circle or those special right triangles.
Right, 30, 60, 90 triangles and 45, 45, 90 triangles.
Exactly.
Okay.
Now we're going to talk about the signs of these functions in the four quadrants of our coordinate system. Remember our unit circle, buddy.
Always.
So in the first quadrant where both x and y are positive, cosine and sine are both positive too.
Makes sense.
And since all the other functions are defined in terms of sine and cosine, they're all positive in the first quadrant too.
Okay.
But as you move to the other quadrants, the signs of x and y change, which affects the signs of the trig functions.
Oh, right, because sometimes x is negative, sometimes y is negative.
Exactly. The source has a table that shows exactly which functions are positive and negative in each quadrant.
That's helpful.
It is figure 3.7, also shows this visually using the unit circle, which is always a good way to think about it.
Yeah, I like that.
Now they talk about the domain and range of each trig function.
Right. Domain is like the allowed inputs and range is the
That's
possible outputs.
Exactly. So sine and cosine are defined for any real number you can plug in,
Yeah.
and their output values always stay between -1 and 1.
Okay.
But the other functions have restrictions on their domains, because remember, they have sine or cosine in the denominator.
Right, so they can't be zero.
Exactly. And their ranges can go to infinity or be specific intervals of real numbers. It's all laid out in a table in the source,
Good to have all that organized.
for sure. And then they describe how sine increases and decreases as the angle changes, starting at 0, going up to 1, back down to the 0, then down to -1, and back up to 0 over a full cycle of 2.
So it's like going around the unit circle watching the coordinate change.
Exactly. And they encourage you to think about how the other functions behave in the same way, using the sine table we just talked about.
Okay.
They briefly mention these things called limits, which are a calculus thing.
Oh, yeah.
It's basically about what happens to a function as its input gets closer and closer to a specific value.
Right, like approaching infinity.
Exactly.
Yeah.
It's relevant here because functions like tangent and secant have those vertical asymptotes where they shoot off to infinity.
Makes sense.
And then they remind us about periodicity. Tangent and cotangents have a period of radians, so they repeat more often than sine, cosine, cosecant, and secant, which all have a period of 2.
Quarter cycles.
Yep. Now, to really see all this in action, they've included graphs of all 6 trig functions in figures 3.8 through 3.13.
Ah, cool. I love graphs.
Yeah, they're super helpful for understanding the big picture. They show the periodic nature, the domains, the ranges. It's all right there.
Visualizing it makes such a difference.
It really does. And then, of course, they have some worked examples. Example 6 shows how to find the values of the other 5 trig functions if you know the value of cosine and what quadrant the angle's in.
Okay.
The quadrant's key because it tells you the signs of the functions.
Right.
They use the identity cosine x plus sin x, one fine sine, and then they just use the definitions of the other functions.
Smart.
Example 7 does the same thing, but starts with cotangent and uses the identity 1 plus coto x equals cosec x.
So it's all about using the right identity.
Exactly.
Yep.
Then examples 8 and 9 show how to use periodicity to deal with really big or negative angles.
Oh, yeah, those can be tricky.
The trick is to reduce those angles to equivalent ones that are between 0 and 2 by adding or subtracting multiples of the period.
Right, get it back into that familiar range.
Exactly. And finally, they point you to exercise 3.2, which is all about practicing evaluating these functions for different angles.
More practice.
Always good. Now we're going to move on to some seriously powerful tools. The trig functions of the sum and difference of 2 angles.
Oh, yeah, I remember those. They get kind of complicated.
They can be, but they're incredibly useful because they let us break down trig functions of combined angles like x plus y or xy into expressions that just use x and y separately.
Right, so you can work with them piece by piece.
Exactly, and that opens up all sorts of possibilities for simplifying things and solving equations.
Makes sense.
So they start with the identity for cosine of a sum.
Hmm.
Cos x plus y, well, cos x goes s twice in x and y.
Okay.
And what's cool is they actually show you how to derive this geometrically using the unit circle and congruent triangles.
Mm-hmm.
It's all there in figure 3.14.
Oh, nice. Proof by picture.
Exactly. And then from there, they get the identity for cosine of a difference.
Yeah.
Cos x cos y plus sin x and y.
So only the sign in the middle changes.
Yeah, that's a pattern you'll see a lot in trig.
Good to know.
They also have these identities called the cofunction identities. Cos 2x is sin x and sin x is cos x.
Oh, X.
These show how sine and cosine are connected for angles that add up to 90 degrees.
Oh, yeah, complementary angles.
Exactly. And then they derive the formulas for sine of a sum and difference. Sin x plus y, sin x goes e plus cos x and y, and sin xy, sin x goes e cos x and y.
Okay, so now we've got all the sum and difference formulas for sine and cosine.
We do. And then they list a bunch of other related identities that you get by plugging specific values into the sum and difference formulas.
Okay.
Like cos plus x, e cos x plus x, sin x cos x, and sin x equals sin x. Those are called reduction formulas.
Reduction because they reduce the angle back to something simpler.
Exactly. And of course, we need formulas for tangents too.
Yeah.
They show that tan x plus y, tan x plus tan y, 1 tan x tan y, and tan x tan y, tan x tan y.
Those are the ones that start to look really complicated.
They do, but they're still super useful, especially when you're dealing with slopes and angles in calculus.
Okay.
And they even give formulas for cotangents, although you don't see those as often.
But it's good to have them just in case.
Totally. Now, here's where it gets even more powerful. By setting y equal to x in the sum formulas, we get the double angle formulas.
Oh, double angle.
Yeah, it means we can write trig functions of 2x using just x. So, for example, cos 2x has 3 common forms. Cos x in by 2 cos x by 1 and 1 2 sin sims. There's even one with just tangents.
Wow, that's a lot.
It is. And we also get sin 2x to sin tangent x and tan 2x, 2 tan x, 1 tan x. These are super important.
They come up a lot.
Oh, yeah, especially in calculus.
Yeah.
And they also mention the triple angle formulas for sine, cosine, and tangents, but they don't go into detail about those here.
Okay.
Then we've got the sum to product formulas, which are like the reverse of the sum and difference formulas. They let you rewrite sums or differences of sines or cosines as products.
Interesting. So it's like going the other way.
Exactly. Like cos x plus cos y can be written as 2 cos x plus y, 2 cos x, y2.
Okay.
These are really helpful for simplifying things and for solving certain kinds of equations.
Makes sense.
And lastly, they list the product to sum formulas, which are basically rearranged versions of the sum and difference formulas.
So you can go back and forth between products and sum.
Exactly. Now, to show us how to use all these identities, they have a ton of examples. Example 10 is about proving a trig equation.
Okay.
They show you how to manipulate one side of the equation using the identities until it matches the other side. It's like solving a puzzle.
Is.
Example 11 uses the difference formula for sine to find the exact value of sin 15 degrees.
Oh, clever.
Yeah, they think of 15 degrees as the difference between 45 degrees and 30 degrees, which are angles we know the sine and cosine of.
That's a neat trick.
Example 12 does the same thing for tan, 13, 12, breaking it down into a sum of simpler angles.
Okay.
Then example 13 is another proof, this time using the tangent, sum, and difference formulas.
More practice.
Example 14 shows this kind of weird relationship between tan x and 2x and tan 3x. It's cool how these identities can reveal hidden connections.
Yeah, that's cool.
Then examples 15, 16, and 17 are all about proving more complicated identities using different combinations of formulas.
So it's getting more challenging.
It is. These examples are great for showing you how to think strategically about which identities to use and how to combine them. And then the source wraps up this section with exercise 3.3, which is full of even more identities for you to try proving.
Awesome. Bring on the challenge.
All right, so now we've got this whole arsenal of trig identities.
Yeah.
We can finally talk about how to solve trig equations.
Okay, that's what we've been building up to.
Exactly.
Okay.
So trig equations are equations where the variable we're trying to solve for is inside a trig function.
Right, like x is inside a sine or a cosine.
Exactly.
Yeah.
And solving them often involves using those identities we just learned to simplify things and isolate the variable.
Makes sense.
Now, the source talks about two types of solutions: principal solutions and general solutions.
Okay, what's the difference?
Principal solutions are just the solutions that fall within one period of the trig function, usually between 0 and 2.
Okay.
And general solutions are expressions that capture all possible solutions, because trig functions are periodic, so they have infinitely many solutions.
Right, they keep repeating.
Exactly. So the general solutions use n to represent any integer to account for that repetition.
Okay.
They start by reminding us of the general solutions for sin x equals 0, which are x equals n, sin equals n plus 1, 2, respectively.
Right, those are the basic ones.
And then they give us 3 theorems that tell us the general solutions for sin x, x sol, x, y, and tan x, tan y. These are like cheat codes for solving these types of equations.
Oh, nice.
Theorem 1 says if sin x equals sin y, then x equals y minus 1e.
Okay.
Theorem 2 says if cos x cos y, then x over 2nh y.
All right.
And theorem 3 says if tan x equals tan y, then x equals n plus y, but only when x and y aren't odd multiples of 2, because that's where tangent is undefined.
Got it.
They even give proofs for these theorems, so we won't go into that here.
Okay.
Then they have a bunch of examples. Example 18 asks for the principal solutions of sin x, 32.
Okay.
They show how to find the two values of x between 0 and 2 that work.
So you find the angles on the unit circle?
Exactly.
Uh,
Example 19 does the same thing, but for tan x equals 1 root over 3. Then examples 20 and 21 ask for the general solutions of sin x, x equals man tree 32, and cov x, x 12, respectively. They use the theorems we just talked about to do this.
so you find one solution and then use the theorem to get all of them?
Precisely. Then example 22 is a bit trickier.
Yeah.
It's tan 2x, covus cod x plus 3.
Oh, yeah, that one looks tough.
The key is to use identities to write everything in terms of just tangents. They use the cofunction identity to change cotangent into tangents.
Okay.
Example 23 is sin 2x, sin 4x plus sin x equals 0. For this one, they use the sum to product formulas to factor the equation, which makes it way easier to solve.
Oh, that's clever. Turn addition into multiplication.
Exactly. And then the last equation, example 24, is 2 cosec x plus 3 sin x equals 0. They use the identity cos x equals 1 sin x to write everything in terms of just sin x, which gives them a quadratic equation they can then solve.
Sometimes you have to manipulate it to get something you know how to solve.
Yep. And then they wrap up this section with exercise 3.4, which is full of practice problems for solving trig equations.
Always good to practice.
For sure. Now, the source has a final set of miscellaneous examples that really test our understanding and show how everything we've learned can be used together.
Okay, a final challenge.
Example 25 gives you sin x and cos y of the quadrants they're in, and asks you to find sin x plus y.
Okay.
So you have to use cos plus sin t1 to find the missing values, and then use the sine sum formula. It's a good test of using multiple concepts together.
Sounds like it.
Example 26 is a really complex identity proof involving half angles. Take some serious algebraic skills to solve this one.
Oh, boy.
Example 27 asks for the exact value of tan, and they use the double angle formula for tangents, but backwards.
Interesting.
Yeah, they use it to find the tangent of half an angle instead of double an angle.
Clever.
Example 28 gives you tan x and its quadrant and asks for sin by 2, cos 2, and tan by 2. You need to use the half angle formulas for this one.
Okay.
And the last example, 29, is another identity proof with squares of cosines and angles that are shifted by 2 3's. It takes some clever manipulation in the sum to product formulas to prove this one.
So it's all about putting all the pieces together.
It is. And then they mention the miscellaneous exercise at the end of chapter 3, which is full of even more challenging problems.
Sounds fun.
All right, so as we wrap up this deep dive, let's take a minute to recap. We started with what angles are and how to measure them in degrees and radians.
Right.
Now, we talked about the unit circle definition of the 6 trig functions and all their important properties. Those key identities, periodicity, domains, and ranges.
Yeah, it was a lot.
It was. And finally, we learned how to solve trig equations using all the tools we've gathered. Expert speaker.